To obtain the notebook in Colab that we will be showing in this video, you can either follow the instructions that are outlined in the description of this video posted on YouTube, or you can simply go to Colab, go to the GitHub option when you go to open up a new notebook or when you're greeted with this screen upon first going to Colab, go to the CU-Denver-MathStats-OER organization, search for the Programming for Data Science repository, and then scroll down a little bit to find the 02 Lecture Part A notebook. That is what you will open, but remember you need to save a copy and then organize it in your repo as discussed in the very first video I made about getting started with Colab. The purpose of the second module in this course is to cover the basics of Python. This is intended only to help break down the barriers of entry into using Python and some of its basic tools commonly used in scientific computing and data science. While we will progress through more advanced topics in this course, no single course or sequence of courses for that matter can possibly cover all that Python has to offer. So I provided some links that I recommend you look through for other tutorials and background on Python in terms of Python basics and other libraries that are really useful for unlocking the power of Python for scientific computing. And remember, we're using Jupyter notebooks for these lectures. Now, as far as this Part A lecture notebook, we have a few learning objectives. We want to, 1, understand some of the more commonly used data types. 2, we want to assign values to variables and perform basic arithmetic operations. Along the way, we'll also really get to understand casting of variables, which is very important. And finally, we will understand how to read error messages to do some basic debugging with mini exercises that are embedded within this notebook. Being able to understand and decipher what an error message is telling you and how you can use that to actually fix code in terms of what's missing or wrong is an incredibly valuable skill, and it's one we should get to right away. Along the way, we are going to use some simple built-in functions within Python. That means you don't have to write anything to use these functions other than just the function name. In particular, we will make use of the functions print, type, and range early on in this lecture. Later on in Module 3, we will get into user-defined functions within Python. This is where you write your own functions and using logic and loops and other types of commands to perform more advanced functionality. We now cover the basics of integers, floats, and some casting. Some key points we're going to cover are that integers are whole numbers, positive or negative or 0, that are specified without decimals. This is key. Examples are 1, 2, 0, and -10. That period right there is the end of the sentence. It is not attached to specify any type of decimal with -10. I will come back to that in just a moment. Floats, which is short for floating point numbers, are finite representations of real numbers on computers that hold a finite number of decimal places after the integer. Examples are 1.1, 2.3, 0.07, and -10.0. Now, in the infinite precision arithmetic that we can do in our head, meaning given enough time with pencil and paper, we can do the computations by hand, we see that -10.0 and -10 are really the same number as far as we're concerned. But as far as the computer is concerned, these are stored as different variable types. An arithmetic operation will cast the result of an operation between variable types as the most general variable used in the operation or as the type of output generally expected from the operation. So whether or not we worry about casting depends upon what result we desire from the operation. We will see later on in this notebook how to easily specify casting. We now move on to some basic examples involving integers, floats, and the casting that occurs of the variable type when we combine them with some simple arithmetic operations. So there's lots of code comments here. You are more than welcome and in fact encouraged to add your own code cells, add or edit the ones that are here. Remember, you can simply put your cursor between any two cells to add either a code or a text cell. You can add your own comments to reflect your understanding or markdown cells that are notes to yourself about things that you're observing. You're really encouraged to make this your own. So let's just go ahead and get into it. You should take the time to really read this stuff carefully. I'm going to do it thoroughly, but at a fairly high level where I won't read all of these code comments. So we first define an integer that is 1. And so we take just the 1 and we store it as the variable 1 underscore int, just to emphasize that this is an integer. And then we are going to take a 1.0 and store it as a variable called 1 underscore float. We are then going to take the number 2, which is an integer because there's no point 0 here, and we're going to store it as 2int, which is going to be a variable as well. So as soon as we run this, and we're telling it to run anyway, I know I made this notebook, it's safe to run. It ran very quickly. You can actually go ahead and hover. Again, this is in Google Colab. You can hover your cursor over the variables and it will tell you that the variable type is an integer for like the 1 underscore int, and then it contains 1, whereas 1 underscore float is a float and has 1.0. Now that's a Colab feature. You won't always be working in Colab throughout your programming experience. So it's important to see how you can also print this information to screen. We can just use the print command. We can use print with no arguments. It's a function, so it needs to have parentheses on it for it to ever work correctly. If you pass it nothing, it will print a blank line. And then if you pass it a argument, and you can separate the types of things that you want it to print with commas, then you can see that it will be printing strings. So strings are just types of arguments that have ticks in front of them. They're meant to be read like text. And so here I want it to print that variable 1 underscore int is of type, and then I want to use the type function to pass it the variable, in which case it will produce the type of that variable. It should produce an int. And 1 float is a type, and then of course now I want it to say after that string, I want it to print the type of 1 float, which of course is a float. So if I run this code cell, then we see that 1 int is of type, and then this is the output of that type command. It is of an integer class. And then the 1 float is of type float. Of course, we already knew this, but I'm just trying to show you how you can use print commands, combine it with some text, which is a type of string formatted variable, although I'm not assigning this to any particular variable output, I'm just printing it. And then I'm using the type command to say, give me the exact type of that variable. It's very useful when you're doing debugging to use type in your code, especially when it gets to be very long, so that you can print types of variables to the screen if the functionality is not working correctly in your code, because you can often find that maybe a variable isn't the type you thought it was due to some sort of just mix-up in the code when you were writing it. So the type and print commands, very useful for debugging. So another thing I show here is that if you insert at any point in the text of a print command, this \n, that stands for new line. And so if I print this, if I run that, you will see that immediately a new line is created. If you compare the output of this print command to this one, the only difference is this \n. Sometimes it makes it harder to read the text because there's no separation between that \n and then the text that comes after it. If I actually put a space right there, which you probably would be tempted to do, I know I am, in order to make this more readable, when I then run that, you see that you have this undesirable space occur right here. So you often have to just put that \n in some place. It makes it a little maybe a little unreadable to to me, but then when you get used to it, you start to just go, oh, that's just a new line, and you kind of start to just ignore it. And it's kind of funny because if you put it anywhere else, and this is where you again can experiment. You're encouraged to do this in these notebooks. Like if I put that \n there, you're going to see what happens. I have this new line right before the 1, and then I put a new line right before the float. So it starts to be a little funny. Of course, you wouldn't do that. You would normally just put it where, the one place you want it, or maybe a few, because maybe you want to break up the text across multiple lines. And then I just show some other examples of printing with the new line commands, just other options. So I won't go over them in the video, but just to provide some blank space so that you can have just more readability of the outputs. Like reading this output is just a little easier than this one because there's a separation of the lines. It's like double spacing. It's just easier on the eyes, makes it a little simpler and more quick to find the information you're looking for when you deliberately introduce white space and blank lines in printed outputs, just like when we do it in code. So the other thing that I'm showing here is how to print the output of like 2int, but now what I'm doing is I'm printing 4 different outputs. And the other things I'm doing are printing the output of 1 int plus 2 int. So that's the summation of two integers. You would probably expect that to be an integer. But if you take an integer and divide it by an integer, or take a float and divide it by an integer, you might be surprised to find that that output is producing a float in both cases. But maybe you're not surprised, because of course often you can divide two integers, like 1 divided by 2. The output is 0.5. That's what you would expect to have happen. And remember, I said one of the key points, the takeaways, is that the casting of an arithmetic operation is generally going to do it based on what the expected output of that operation is going to be. The other thing that you can see is that addition, though, is a little bit different. If I add 1 int and 1 int, that gives me 2. But if I add 1 int to 1 float, that's going to give me a float. You're going to see the outputs here. So 1 int plus 1 int is 1 plus 1 is 2. But this is 1 plus 1.0, and it gives me 2.0. So the output of this is of the more general type. Even though 2.0 arithmetically is no different than 2, the computer is going to treat it like a different type entirely. It's going to treat it like a floating point. Now, this is important because sometimes we're adding numbers together that could be the result of other operations that produced floats, but we're expecting integers when we're doing things like looping, where we're expecting the iterable object to be something like an integer. So sometimes this can produce an undesirable output in code, and that's where type checking when you're doing debugging is useful. And then you might find I need to force this to be, instead of 2.0, 2. And that's something we'll cover in a little bit in this video. We've already seen that division will generally produce a float as an output when we're dividing either integers or floating point numbers together, or a float and an int if we're mixing variable types, because it expects the output to be of a floating point type. However, there are different things that you can do to force integer division. So like if you want to get rid of any of the decimal places. So that's provided in this part of the notebook. I don't want to provide much commentary on it other than to just run these. And I want to encourage you to do this for yourself, run through these and add additional code comments, or break up these cells, split them up and add some markdown cells to just comment what you're seeing and your understanding of what's going on. I have some comments here, but this is a good part for you to try to go through on your own and really try to understand how this standard division is different than what is this integer or floor division. This instructor-led activity involves reading error messages and fixing code. It is intended to help you solve activity 1 on your own. I, in fact, encourage you to pause the video now and try to solve this instructor-led activity on your own, and then watch the rest of this video so that you can see if you caught all the things that I did, at least in terms of additional comments and observations that I made while you try to solve it on your own. The solution video for activity 1 will not be a part of this video. It is separate, and it will be in the playlist that is associated with these videos on YouTube, and I will also link to it on Canvas. As to this instructor-led activity, before we even go to solve it, I want to point out a few things. First of all, in Colab, it's very good about trying to determine where there are possible errors by providing kind of these red squiggly underlines. And you will also notice that it will provide some red vertical bars associated with those lines over on the right-hand side of the code cell, on the very far right. And so that's pretty cool. The Colab has that nice feature. That's not a standard thing you would see in a traditional Jupyter Notebook environment or in the Jupyter Lab environment. And another thing is that there's line numbers by default already shown here. When we see error messages, the error message will be associated with a particular line of code, and the line number will be reported. So having these line numbers reported shown, made visible by Colab, is very useful to us as we try to debug code and figure out what's going on when we receive error messages. So there's different types of errors. Let's go ahead and run this and go ahead and see what type of first error we get. We see that at line 2, we got an error that is a syntax error. There's an invalid syntax. It was expecting something to be written in a different way. In fact, we see that the variable 1/2 is not assigned anything. It's equal to nothing. We haven't written anything there. And that's not proper syntax. The proper syntax is to actually assign a variable some value. Well, you can see from the code comment, it's pretty clear we intend to make 0.5 equal to 1/2, which is the same thing as the output of 1 divided by 2. You could also write 1 divided by 2 here. You could also write 1 int divided by 2 int, right? There's various different ways to do this. It's up to you. We can go ahead and have 1 int over 2 int because that's associated with this print statement, or you look at the code comment and make this equal to 0.5, which we know is the output of 1 int over 2 int based on the earlier part of the code that we see up here. So let's just do that. Let's make this 1 int over 2 int just for the sake of argument. Let's just see what happens. Well, when we run this, we see that now we get an error on line 9. You could say, why didn't we see that error before? Well, on line 9, that is happening after line 2. And when the code reaches an error, when it's attempted to be executed by the runtime, the Python kernel that's running in the background, as soon as it encounters an error, it just stops. It can't continue on in the code. And so that's why we saw an error at line 2, but we weren't made aware of any future errors. And you can see here, well, we are clearly intending this to be something like 1 divided by 2 with the floor division that was explored earlier in this notebook, just above this. And so this was 1 int divided by 2 int. So I'll just go ahead and do it that way. Now, if I put that in there, and you can see that the red squiggly lines have disappeared here, and also these red vertical lines have either disappeared or shrunken. So we've resolved these errors, but we can't know for sure until we actually try to run the code cell. Now we see that we have an error on line 11. And on line 11, we have this print statement, and you see that this caret is pointing to where the error generally is, and it's saying, well, it's right here at type. And you might look at this and say, oh, let me zoom out, excuse me. When we look at this type function, we're not passing it a variable to ask, or an object to ask what type of variable it is, give us information about it. So you might think that's where the error is because the caret seems to be pointing at type. But this is a syntax error. This is where it's sometimes useful to go to, I believe it is the scratch cell, insert a scratch cell. Yeah, so we want to go to insert scratch code cell. You could just try type by itself to see, does that produce the type of error that I'm seeing there? This is a good use of the scratch cell. You say, no, this produces a type error because the type function takes arguments. It takes, objects, and it returns information about them. So this is not the source of the error. So this might be a little confusing. If you look at this, one of the things that you start to notice is that we are separating different pieces that we're printing with commas. And we are missing a comma here. And this caret pointing to type is saying it wasn't expecting the word type to appear. It's not pointing into the parentheses, and it's not giving a type error. This fixes that syntax error. Now, if I run this, I have an error again at line 11. Right? Now it's pointing directly to line 11. So this is just different, right? When it's a syntax error, you get the line number and you get this little caret symbol that is pointing upwards towards where the syntax error appears to be in that line of code. Now we're getting a different type of output display for the error, where we have an arrow pointing to line 11, and we're told that we have a type error, that the type function takes 1 or 3 arguments. And it's pretty clear from reading the statement that what is intended to be written here is not 1/2 as the variable into type. And if we run this now it runs free of errors. So that's it. That solves the errors, and we've systematically fixed all of them in this instructor-led activity. You'll notice there's no more red bars showing up. There's just Google Colab is not predicting any potential problems with this code. I do want to draw your attention to one final thing though before we end this section of the video, and that's this vertical line that's right here in the code cell. You can say, what is the purpose of that? Well, you can completely ignore it if you want, and it's fine to ignore it. It won't cause any errors if you ignore it, in fact, right? We just ran the code cell with no errors. But in general, you want to avoid overly long lines of code, meaning that if I have a lot of characters in my code, I don't necessarily want it to be something that I have to scroll from left to right through to read. I don't want to have to be doing a lot of scrolling left to right. I want to look at things more up, down. So it's a good idea to try to structure your code so that if you have a long code statement, you break it up across multiple lines. Inside of a function like print, when you're separating things with commas are great places where you can press enter, and then it's just going to continue on and with this part of the code. And so I'm going to do that here as well. And it's just a nice way to break up a super long line of code. Even though these maybe don't look super long, this is kind of a suggested formatting where you don't go beyond this line with your code comments or your actual lines of code. Sometimes it can't be avoided. In that case, you just deal with it. You just live with it. But if you can avoid it, it's kind of better formatting. It's better practice. Now so I'll just show you. If I run this, I get exactly the same output. It's not like separating out these statements on different lines, printed different lines with that print statement. That's all still right here. What it did was it just ran. Now it was important that I had enter after that comma. If I get rid of that comma and just place it here, right? Now when I run this, oh, actually that was fine. I thought that was going to give an error. I think it might have used to on an older version of Python that I used to run on. But I think that looks weird if you don't do it after the comma. So my practice is to always do it after the comma. But there you go. Like I said, I'm always learning new things. I really thought that would have produced an error. I thought it did in the past, but not anymore. So that's it for this part of the video, but we'll continue on shortly. The user can specify casting as well. So we've seen some floor division above, and we've seen that there can be particular guesses at what the output should be from Python. Like if you divide two integers, it's expecting the output to be a float. So by default, the type of the variable that is the output will be a float. But you can actually control the outputs in a fairly heavy-handed way, or maybe a more targeted way, as you need to within your code, and this is what's called user-specified casting. The key points are that we can specify how we want an integer or a float to be treated to allow for greater control in the code. This is also referred to as casting whenever we specify that a variable should be treated as a different type from what it is in a particular context. We show just two functions for casting below, int and float, but there are more. And I ask you, can you find another one used later in the notebook? There is another one. Note that casting a variable as a different type does not actually alter the original variable type. So here, what I'm doing is I'm taking 2, right, the number 2, and I'm adding the integer 1 and the float 1 together. Now, when I add an int and a float, it's going to cast that as the more general type, which is a float. So this variable 2 will now be 2.0, and it will be of type float, which is what we see here. It's 2.0. But if you wanted the output of that to be an integer, for whatever reason, and there's certainly good reasons to have outputs involving floats be integers. If you maybe say like, well, I know that the output is 2.0, but I need it to be 2 because maybe I'm specifying the number of integer times I loop through something based on that result. Well, then what you can do is you can use int as a function. So you take int, which is going to be your function. You have parentheses here. It's very important to have the parentheses, and you pass one float into the function int. That is now casting one float as an int for the purpose of this operation. This will now change the variable 2 to just 2, not 2.0, but 2, which is an int. And it does not change the original variable, one float. It will still be a float. So let's go ahead and run this code to see. And you see that's exactly what happened. The variable 2 is 2 of class int, but one float is still of class float. If we take x to be, let's say, negative 3.7, and we do a similar thing here, then we'll run the type. So let me just go ahead and run this code cell, and then we'll go over the outputs. So x is negative 3.7, and then we print it, and we say what type it is. Well, of course, it's of type float. If we look at int of x, that should, of course, be an integer. But we can also change integers to floats. And I'm just printing blank lines in between these different print statements. So here I'm taking float of one int. And so now that one int, which is just 1, it wasn't 1.0. But if I cast it for the purpose of this operation, just right here as part of this print statement, then it prints like 1.0. So you can use float and int and other types of variable types to do specific casting when you need to have greater control and flexibility within your code. Raising a variable to a power is done using two time symbols back to back. It is not done using the caret symbol that you might be familiar with from other types of computational devices or programming languages you've used in the past. As an example of this, let's look at the variable that is stored as 0.1. So it is 0.1. If we cube it, then we do point_1, that's the variable name, raised to the third power. This is how this is read. And so if you take 0.1 and you raise it to the third power, what should that be? That should be 0.001. Now notice it also has a whole bunch of other zeros and then a 2 at the end. And you might say, what's going on with that? 0.1 cubed, which is 1/10 cubed, is 1/1000th, which is 0.001. Why is there this 2 hanging out at the end with so many zeros between it and the 1? Well, this is a consequence of the finite precision arithmetic that's done on a computer. Only so many decimal places are stored in memory, and they're stored in binary for everything. So it's zeros and ones are what are used to store everything. And this can result in some extraneous little values that are associated with your computations that are just round off errors. Just the errors that are associated with doing computations and arithmetic on a computer. So computers are very fast at getting you results compared to doing computations by hand, but they actually come with a trade-off in that a lot of computations are not exact, they're approximate. So that's just something that's good to keep in mind, which is why I like this example. So what about complex valued variables? If it just so happens that you need to deal with complex numbers, then it's important to remember that Python uses the electrical engineering J convention to denote the imaginary components. In other words, J is the square root of -1. You might be used to it being I, but in fact in Python, also in MATLAB, I believe, J is what is used for -1. Now, how is this used in practice? Well, the way it's done in practice, so I'm going to zoom out here, is that the letter J can still be used as a variable for another number with no issues. So what you do is instead of saying you multiply by the square root of -1 to make a negative number, you actually just append it. You just have it exactly after the number. So this is different. I'm going to fix the formatting because remember, proper comments should have 2 spaces before the hash symbol, the pound symbol, and then you should have your comment. So I just fixed that right there. So we can make J to be something like, 3.684. I'm just making it something that's just nonsense, but it's clearly not the square root of -1. And then I'm taking the number alpha and I'm making it equal to 3 minus 4J. Now this is not the same thing. It is not equal to 3 times 4J, 3 minus 4 times J, which is what I'm doing right here. So I'm just showing this. I'm showing you what the type of alpha is. I'm taking the absolute value of alpha. So absolute value is a function. That's a math function that's just built in with the Python that you can use. It returns the absolute value of the argument. And I'm showing you what that does when you give it a complex number. And then I'm also going to show you that if J is equal to, in this case, 3.68439876, then 3 minus 4 times J is clearly different than 3 minus 4J. So let's just go ahead and run this code cell and see these outputs. So we see that alpha, 3 minus 4J, is a complex number. It's of class complex. So it's not an int, it's not a float, it's complex. We see that 3 minus 4J has length 5. That's the absolute value. And you might say, 5? There's a 3 and a 4 there. The magnitude or absolute value of a complex number is given by the square root of the sum of squares of the real and imaginary components. So 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. The square root of 25 is 5. That's the absolute value of that complex number. And then, of course, you see that 3 minus 4 times J, where J is this 3.68 thing. It's just something else entirely. It's just this float number that is clearly not this complex number, and the absolute value of that is going to clearly not be 5. What about strings? This is another type of variable. Many binary operations do not apply to strings, but one can still do the plus symbol to do concatenation between 2 strings. Concatenation is particularly useful when creating file names for saving and loading data that's generated in loops, or to just have based on different runs of a code. I use this actually a lot. We can also create multiples of text, so we can do times. So here's some options just to show you this. If I make the text variable equal to hello, and that's a string. What makes it a string is there's this tick mark here and this tick mark here. It's enclosed in strings. You can also do 2, but they need to match. So it's 2 and 2. That'll also work. If it was just one vertical tick and a set of quotes, then that would produce an error. So you have the single set of quotes or single set of tick marks. And then what I'm doing is I'm saying text, this is equivalent. I'm going to fix my comment formatting, this is equivalent to text equals text plus. And so I'm actually plus, and then here's the string, right, that I would give it there. So this is just a shorter way to basically add something to this variable and store it as that variable. Text is plus equals, that means text equals text plus world. It's called an in-place operation, but that's something, why it's in place, what does that mean? We will actually get to that in a future lecture. For now, just know that this is the same thing as writing text equals text plus and then world. So we're making the variable say hello world, and then we're going to print it. We're then going to take this text and we're going to multiply it by 3 and store that in text again. So again, this is the same as text equals 3 times text, or at least it accomplishes the same thing. It's technically different in that this is not an in-place operator, but again, what that means, we'll get to that later. So let's just go ahead and run this. And we see that here's hello world. That's the result of this first operation where we added a string to a string. And then when we multiply the string by an integer, we see hello world, hello world, hello world 3 times. Now you could say, what would happen if I multiply this by 3.0? You cannot multiply the sequence by a non-int of type float. What this is, so this is a type error. And again, this is something that you should be doing. You should be experimenting with all of this stuff and seeing for yourself, what would happen if I tried something different? Well, you can't take a string and multiply it by a float. It's got to be an integer. So 3 is okay. I believe 0 is okay. Right now it just prints nothing. 2 is okay, right? You could say, well, what? Okay, negative 2 is an integer. True. That's going to have the same impact as 0, apparently. I didn't know that. I was just trying it because this is what you should do. I was just curious. I didn't actually know what would happen because I would never think to multiply a string by a negative integer. But apparently it has the same impact as multiplying by 0. But let's just go ahead and change that back to 3. So there we go. Now, there's some additional things here. I'm not going to go over this in the video. I'm just showing different types of casting where I'm assigning like a string of 1 as an int, and then I'm doing things with floats and string, just very specific user casting, and these other parts of casting and some expressions, just some evaluations of things as well. Oh, I'll actually get to this. I'll run this. So I've generated some different code, but I want to go to this cell. I'll say something about this one. Sometimes we want to evaluate mathematical expressions that are stored as strings. And for that, the eval function is useful. So this is worth me discussing. These other code cells are just more examples for you to play with and for you to kind of think about what the outputs are going to be before you run the code. But let's go ahead and look at this one. Here, right, I have this expression, 1 float plus 1 float. So I'm adding variables together that I do have assigned as some numbers up above in this notebook. And what I'm doing is creating an expression based on the variable names, but it's as a string. And so if I print what that is, it will print just like this. It'll print 1 float plus 1 float. But if I print the evaluation of this expression, then what it should do is add 1 and 1 together. And because they're both floats, that should be 2.0. And so that's exactly what you see happen. So the eval is very useful when you need to evaluate the output of a string. In fact, you can hover your cursor over there and it says what it will do. The source may be a string representing a Python expression or a code object as returned. Anyways, that may seem like a bunch of gobbledygook, but the point is it's sometimes very useful when you have a string expression involving variables and there's a mathematical expression in that string and you would like to evaluate it, use eval. That's it. In this instructor-led activity, we have some more practice with casting and printing. You are to use the comments in the code cell below to help fill in the missing pieces of the code that creates and prints the string variable str_var, which is meant to be read in your head as string variable. Now, I again recommend you try to pause this video and do this for yourself, and then watch me do this. All right, so we see on the line 1, we create x, and x is a string 0.5. We are to cast x as a float and then cast as a string. So cast x as a float and then cast as a string. So x is a float and then a string. Okay, so we want to cast as a float first, so say float of x. Then you want to cast it as a string. So that has to be done next. So the way this works is it goes inside out. The inner function is done first, that's the float, and then we're casting this as a string. Here, we want to cast x as an integer and then cast as a string. You need to use eval here. So let's just go ahead and let me just run this so far. Okay, so notice we have this error on line 7, so it at least ran through line 4. But we haven't done anything here, and of course it's a syntax error because there's something that's supposed to be on the right of an equal sign. So let's look at doing the same thing like I did before, where I did string int x. All right. So if I try to do this, look what happens. It's a value error. This is an invalid literal for int with base 10. Like you might look at that and go, what does that mean? Well, the issue here is that you tried to cast x as an int, but x wasn't like an integer string to begin with. It was 0.5. So what we need to do, right, the int is expecting a float. So float apparently works on a string to cast like a string number, like a 0.5 into a float, but int does not. You need to actually use that eval function that we talked about first, or not first, but before this moment of the video, and that will evaluate x as 0.5. We will then cast it as an int, and then we will cast it as a string. So now when we run this, we get all the outputs, I believe, that we want from this, and we see that the string variable, which is x plus, right, the rest of this, and then we have some new lines to be printed out. Excuse me. When we print the string variable, you can read through what this is, and we're using that plus equal again. But what we're saying is 0.5 is the variable we start with, which is then turned into the float 0.5, right? But we are making that float into a string so that we can just print it as one long string, because we're adding all of these things together. They all need to be of the same type. They need to be strings. And we're even, when we do this plus equals here, notice that we have a string, and then we have plus another string variable. This is important. If I had left this as float, no, not float, and then I'll just leave it as, so it's x float string. I won't change the name of the variable. If I run this, you will see this is a type error. You can only concatenate, which means to add a string to a string. You can't do it with a float. That's a very readable error given by Python. Sometimes the errors are somewhat indecipherable, and you just look at the line number and the type of the error, in this case a type error, and you say, okay, that's the wrong variable type. You could fix that by casting this right here as a string. Of course, that defeats the purpose of the variable name and what we were actually asked to do here. So I'm going to just go back to this, make that a string. All right. And go back to the output that we saw, which is that 0.5 is the variable we started with, which is then turned into the float 0.5, and is also turned into the int 0. And it's turned into the int 0 with the help of the eval function. And maybe this is something I recommend you doing if you're watching the video and you're following along. Add a new line of code, maybe right here, put it on line 15, and make it so it says, so it adds to the end of this with the help of the eval function. Do that. That's a good little exercise for you. We have now created quite a few variables that are stored in memory. So let us take a second and discuss how we can view what variables there are and their types in a convenient way. There's some key points here. We are going to use a magic command, in fact, our first magic command that we've seen. In IPython, which is interactive Python, which is what's being run in this Jupyter Notebook environment, that's the kernel, is an interactive Python kernel. Magic commands are conveniently prefaced by a % symbol. If you run these commands in a non-interactive Python environment, they will not work. You typically only include these commands as you are debugging code in an interactive environment such as IPython terminal or a Jupyter Notebook like this. The whos command with the % in front of it is particularly useful for debugging as it returns all variables in memory along with their type. So right here, if I do this, if I run it, you will see all the variables we've created so far that have been of this code cell in the notebook. You will see their type, and you will also see some additional data and info about that type. There are other magic commands available to you. You can use the ls magic for list magic, and it will tell you all the available magics. Now, we used a line magic with that %. There's also cell magics. If you want to understand what a cell magic is, I recommend Google. We won't be really using these in this course. Another thing I want to point out is in Colab, there's this little symbol over here. It's in the left pane. It's the second one up. So there's a files, and then there's variables, and then you can find and replace, which is also useful. And there's that table of contents that I haven't looked at yet. I haven't opened it up in this notebook, but I showed you in the lecture 1 video. If you click on the variables icon, this will do effectively the same thing that we saw with whos, although you'll see there's some other information here in terms of like shape, and there's the value, and you see that value is kind of long because of it. You can resize this if you need to make it larger. So that's useful. You can also filter variables. So that's also useful. You don't need the whos. The whos is just an example. But if you weren't in Colab, you might want to use whos to check out the variables. It just so happens that in Colab, you have that nice option. We now discuss Python lists. Here are some key points about Python lists. Lists are ordered arrays of almost any type of variable. You can even mix variable types within a list. You can in fact even make a list of lists. You use lists when the order matters in the code. For example, when you plan on iterating or looping through the elements of the list in some ordered way. Other data structures that are popular in Python that we really don't talk about in this course are dictionaries and sets. We will see dictionaries a little bit later on, as well as some tuples in an assignment, and I talk about it a little bit lower in the notebook, but I'm not going to talk about them in this video. Indexing starts at 0. This is a very important property of lists. This means that the very first element of a list is indexed by a 0. The second element is indexed by 1, and so on. If that seems confusing at first, don't worry, you'll get used to it. We're now going to look at some examples. Our first example of a list is this float list that contains the floats 1, 2, and 3. We will print it to the screen as well as the type of that variable so that you can see that it is indeed a list. We will then multiply the list by 2. What do you think this should produce? Should it produce a list that has the elements 2, 4, and 6? Or should it produce 2 copies of the list, like what happened when we multiplied a string by a number? We also show that the indexing starts at 0, that this should produce the first element of float list, which is the number 1. We then multiply that by 2, and we show that none of these operations, multiplying the list by 2 or multiplying an element of the list by 2, actually change the list by printing that to screen. So we now run this code cell, and we see that our float list is 1, 2, 3. It is of type list. When we multiply float list by 2, we see that we produce a single list that has the elements of the list repeated twice in order. So it goes 1, 2, 3, 1, 2, 3. If we had done float list times 3, we would have seen 1, 2, 3, 1, 2, 3, 1, 2, 3 in a single list. The first element of the list, again indexed by 0, is 1.0. Of course, you can multiply that by anything you like, and then that doesn't change what the actual elements of the list are. Our second example for a list is created using the range function. The range function is useful for creating an object that can be iterated over from a starting point to some ending point by a certain step size. While it does not create a list, it can be used to quickly create lists of ordered numbers as I show below. So first, I just have the range function. I'm starting from 1, going to 20, and I'm doing it in steps of 2. I'm going to print a blank line after I print what that range is, and then I'm going to print what the type is. So what you see is when I print range 122, it just produces this, and it's of class range. So that's not a list at all. But if we make a list out of it, meaning we cast the range object as a list, and let me just fix the formatting on my comment there, this will create an integer list. And we then print that integer list below, and as well as its type. So if you look at the type of the int list and the type of the float list, that was the 1, 2, 3 of our first example, they're both lists. So it doesn't matter that the inputs of one are an int and the inputs of another are a float. They're just considered of class or type list. The int list, as you can see, goes from 1 to 20 in steps of 2. And of course, when you go from 1 to 20 in steps of 2, you go 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. 21 would be the next one, but we're stopping at 20. So 20 doesn't actually appear in that list when we created it using that range function. Our third example of list is a list of lists. Here we're taking the float list and the int list as the first and second arguments of the list of lists. We then say that this is a mixed list. Of course, I should probably just say list of lists here, and I say what it is. But then I say, well, what's the first component of this list of lists? Well, in fact, that is the float list. So this first component should be the entire float list. The second component, which we get using the 1 here, because again, Python indexing starts at 0, is going to be the int list. So you see that this list of lists can contain lists that are completely different sizes from each other. To access the individual components of these different lists, you then use a different set of square brackets, and then you put an index in there. You can use 0, 1, or 2 for the float list, and then you can use, let's see here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 for the int list. So it has 10 numbers, but the indexing starts at 0, so you can go from 0 to 9. So I recommend you play around with that. That would be a good use of a scratch cell to play around with the outputs and just check that out for yourself. But I'm just going to run this and show you. The mixed list, you see this list of lists, pay attention to the square brackets. You see 2 pairs because it's actually just one outer pair, and then the different components are grouped together with those square brackets indicating the first list, which was the float list, and the second list, which was the int list. The first component of my mixed list is that float list. The second component of my int list, because again, Python indexing starts at 0, I know I've repeated that a few times, is this int list. And then the second component of my first object, my first component of my mixed list, will be this, right? Because it's 0, 1. So the first component, which is indexed by 0, is 1. The second component is indexed by the first component is indexed by 0, the second component is indexed by 1. Sorry if I mixed that up a little bit. And then here you see, of course, this is the third component of this list, which is the 5. We end our examples of list with this concatenation of list. We use the addition, and much like with strings, we form a concatenation. It just adds the contents of one list to the end of another. So this concatenated list, which is int list plus float list, will then produce the following result. It has the integers first from 1 to 19 in steps of 2, and then it goes 1.0, 2.0, 3.0, the contents of the float list. But notice that this is a single list, which is very different than the mixed list of lists that we had from our previous example. We end this video with just a few quick notes about lists. While we can build a list of numbers like we've shown above, their group behavior does not match the individual behavior. For example, float list times 2 produces a list of floats that is not equal to the floats within the list multiplied by 2. In another notebook, we will work with NumPy arrays, which are lists that behave more like vectors and matrices. Generally, if the objective is to do actual scientific computations on the list that are like matrix or vector operations, then you really want to use NumPy arrays, not lists. If you have any experience with MATLAB, then working with NumPy should feel far more natural. In your assignment, you will be exposed to more on list with a focus on some useful manipulations of this data type. List comprehensions are special ways of creating lists using loops, functions, and logic. Since those are topics for a future lecture, we only mention this here. The assignment for the next lecture will return to the specific topic. There's also some notes I have here about dictionaries and other data types like a tuple and how a zip can be used. You will encounter a little bit of this in your homework assignment. You should read through this content carefully and do your own explorations, and you can input new code cells here. You could use scratch cells. I really encourage you to make this your own and start your exploration. And then don't forget to do the activity at the very end. Read the instructions very carefully. That's it for this video. Thanks for watching.